to continue with the chapter that we have. So as I remind you, the deadline for chapter 17 is today. And then I put chapter 18 for next week. And then if we finish chapter 19 by Thursday, so the deadline will be on next Thursday. Okay. So I'm going to give you the schedule of the remaining what we call class, because most likely after today we might meet at least twice. Okay, and then it's goodbye for us. Okay, or I mean, at least for me. Okay, I'm saying bye bye to you, and the only time you're going to meet me is on what we call, if you are a major in chemistry, biochemistry, or forensic science, because there's a course there that I'm the only one teaching. And I also like to invite the majors that we have, the chemistry, biochemistry, and forensic science for the meeting for advice tomorrow. So the Zoom details is already posted in our classes. Okay, so if you're a chemistry, biochemistry, and forensic science, I want you to attend to it. If you are not any of those majors, don't attend, because even those majors who will attend to it, they will not be given what we call bonus points. Okay, they are asked to attend to it so they will know what they're going to do for their registration next semester, for next semester, when you took what your orgo. Okay, so you will be advised what are the courses that you're going to take last time. So we have started already with chapter 19, and we discussed about the so-called electrochemistry. So we said the electrochemical process that we have here is just the redox reactions that we have known since chapter 4. Okay, so I gave you this acronym to help you remind or remember what does oxidation and reduction mean. So in two words, they just what we call uh, electron transfer reaction. Okay, so if you're going to what we call look at any redox reaction, the thing that you need to look at is the change in their so-called oxidation number. Okay, so in an electrochemical process, two things can happen. Either the energy is produced by a spontaneous reaction, or you're going to need energy to make a non-spontaneous reaction happen, or to make a non-spontaneous reaction to occur. So the Monday lab, uh, some of you who did the experiment, you're able to observe it. One wherein you have what we call a copper and a zinc metal dip in the respective solution. You dip them, okay, and you produce energy as measured by the voltage. Now the other one, you use a battery wherein you're going to react your Ki. So what does the Ki produce? To those who attended or performed the experiment yesterday, in two electrodes, you observe the formation of a brown solution, which is your iodine, and the generation of bubbles, which is your hydrogen. So that's the what we call electrochemical process that can happen. And we have reviewed last time about the so-called oxidation number. Okay, so what we're going to do today is we're going to continue on this lesson wherein we're doing the balancing of the redox reaction. Now, except for this one, you're already familiar with what? Balancing equation. What's the main law that dictates the balance equation? Anyone? What is the law that is behind the balance equation? Anyone? Okay. Law of conservation of mass tells us that whatever is the number of the reactants, that is also be the number of the products, or whatever the number of the elements in the reactant side, they should be the same as the product side. Now, unlike the typical balance equation, all we need to do is to monitor what? That the number of the reactants on both sides are the same. But if you put redox into action, you also have to consider that the electron transfer are the same. What does it mean? The number of electrons that was lost is also equal to the number of electrons that was gained. So that's the additional, we could say, characteristic or properties redox reaction has, or balancing redox reactions mean. Okay, so let's try to do some balancing. So I think the next we could say 20 minutes is just all balancing. So you have here the oxidation of Fe2 plus to Fe3 plus by dichromate in acidic solution. So what does this mean? How are we going to balance this equation? So the first thing that we're going to do is write the skeletal reaction. So you write the unbalanced equation for the reaction in ionic form. So there's a mistake there. That should be in, not ion. And if you're going to look at this, this is how the reactions looks like. Your Fe2 plus converted to Fe3 plus, and then your dichromate producing chromium 3 plus. Now the question here now, which one is oxidized and which one is reduced? Although the next sequences tells you Fe2 plus is the one that is oxidized while chromium is the one that is reduced, you have to know why. Okay, so it has something to do with the oxidation number. So you have a positive 2 sign here, so that means the oxidation number is +2. This one is 3 plus, so that means the oxidation number is +3. So that means there's a loss of 1 electrons from Fe2 plus to Fe3 plus. Now dichromate on the other hand, if you follow here, is a -2 net charge. So that means if this is a -2 times 14, so that will give times 7 will give you -14. So that means each chromium there will have +6, because 6 times 2 will give you 12. Add it with -14, you get a -2. And the charge here, that's the oxidation number. So as you're going to see here, there's 1 electron that was lost, hence it was oxidized. And there are what? 3 electrons, okay, that was gained, so that was reduced. Now, the way that you're going to balance this one is you're going to separate the oxidation and the reduction reaction. Okay, so the way that you're going to do it is the half reaction. So you're going to balance it using half reaction. And the first thing that you're going to balance is all elements except O and hydrogen. So this is the difference in terms of the balancing redox compared to the ordinary reaction. You have to consider O and hydrogen. Okay, so I think the only thing that's not balanced here is the chromium, because you could see 1 Fe and then there's another 1 Fe in the both sides. Okay, but here you have what? 2 Cr, but here you only have 1. So you balance them, you have this. So at this time, all sides are what we call balance in terms of the number of elements. That's where the ordinary reaction ends, but not here. That's just only the beginning. So what we're going to do, you will see that we have a hydrogen here. Oh, not the hydrogen. We have an oxygen here. So how are we going to balance this oxygen? So the rule that they have there, for every oxygen to be balanced, you have to add water that corresponds to the number of oxygen in the other side. So if you have that, what we call 7 oxygen here, you're going to add what? 7 water. Now, when you add 7 water, you also introducing hydrogen. Okay, So how many hydrogen did you add on this side? So 7 water, so that's 7 oxygens to balance it. So you also introduce 14 hydrogen that you're going to add now on the other side as H plus. Okay, so add water to balance oxygen and then add H plus to balance the hydrogen atom. So this is now the other side. The other side, you don't need to do anything because it's just like this. Not CR, the FE. You don't have to do anything because it is balanced now in terms of the element. Now here, they're now balanced in terms of the element. So the next thing that you're going to do is make sure the electrons are balanced. So what does it mean? The loss of electrons is the same as the gain of electrons. And you're going to do it by half reaction. So you have a +2 here. You have a +3 here. How are you going to balance them? You add an electron on this side. So both sides now will have what charge? Anyone? So both of them will now have +2. Okay? So the next thing that we're going to do is the other side. So how did I end up with the 6 there? So most likely it's on the charge. So if you're going to look at this, the charge that we have on this side is 2 times 3 plus, that's +6. And on this side, you have what? 14, okay, plus -2 will give you what? 14 plus -2, that will give you what? 12. So how are you going to make both 6? You're going to add 6 electrons. So 12 plus -6 will give you 6. So both sides now are the same in terms of charge. So what are we going to do next? You have to make sure that the exchange is the same. So here you only have what? 1 electron, and here you have 6 electrons. So it's not balanced. So what are you going to do? Okay. So what you're going to do here is you're going to multiply this by 6. Why? So that it will have the same number of electrons that was gained. Okay, so if you have this what we call reaction, you just cancel out what you can cancel out, and then you bring down everything. So you end up with this what we call reaction. And if you want to verify how much you have on both sides, so you have to verify the number of atoms and the charges and make sure they're balanced. And to do that, what do you do? So you have 14 H plus here. Here 7 times 2, that's 14. 2 chromium, 2 chromium, 7 oxygen, 7 oxygen, 6 Fe, 6 Fe. Now in terms of charge, so this is what? 14 plus -2 plus 6 times 2, that's what? 12. So what's the charge that you have here? 24. And then here you have what? 6 times 3, that's 18, plus 2 times 3 plus 6, so you also have 24. Now what do we do? Now that we verify them to be what we call the same number of elements on both sides, the same charges on both sides, so we could say this is the balance equation. And it is an acidic solution because you have an H plus here. Question? Question? Now, what happened if we are going to balance them in basic solution? So what are we going to do? So I'm going to just close this one so I can use the same slide. that I have. And then so it says here, I'm going to add hydroxide to both sides of equation for every H plus that appears in the final equation. So what does this mean if I want this to be in hydroxide or basic solution? So I'm going to add what? 14 hydroxide here, which I'm going to add also on this side. So what will happen? 14 hydroxide and 14 H plus. What will happen? This will become what? Anyone? 14H plus added with 14OH minus. What does it become? So it becomes 14 water. And then I have 7 here. So that means I cancel out this one, leaving me with this one as 7. And then this is my balanced chemical equation in basic solution. So if you're going to look at the changes that you have, Cr2 is still 2, Cr is still 2, oxygen here is 7 plus 7 here, that will be 14, so 14 here for oxygen. Fe is still what we call 6, and hydrogen 7 times 2 is what we call 14, which also have this one. So this is what we call the basic solution. Okay, so let's try other problem like this one. How are we going to solve this? Dichromate ion in acidic solution is an oxidizing agent. When it reacts with zinc, the metal is oxidized to zinc. And nitrate is reduced.
You're not sharing your screen with us.
Okay, just wait. Where it goes. So this one is shared now.
Yeah, we can see it now. Thanks.
So before we do this one, because I wasn't able to share the thing, so how do we make it into a basic solution? So what I did here is I just add what? 14 OH minus. And if I have 14 H plus and 14 OH, I have 14 water. And what will I do? I also add 14 OH minus on this side. So I cancel out the water here. So this becomes only 7. So everything is the same. So I still have 7 times 2, 14 hydrogen here, which is the same here. And then 7 oxygen here plus 7 oxygen here, 14 oxygen. That's it, 14 oxygen. So this is the one in basic solution. Okay. So the next problem that we have is this one. So you have a zinc metal there that is oxidized to zinc 2 plus and the nitrate is reduced. Assume that the dichromate, okay, is reduced to chromium 3 plus. So if we're going to look at this, okay, the reaction that we have here is what? Dichromate reacting with zinc. This should be dichromate. Okay, I think there's something wrong with the statement that we have here. So the dichromate is reduced. So if you're going to look at the reaction here, this is a reaction of what? Cr2O7, 2 minus, reacting with zinc, producing Cr3 plus and zinc 2 plus. So if we're going to divide them, so we could have what? This one zinc producing zinc 2 plus, and we have Cr2O7, 2 minus, producing Cr3 plus. So which one is oxidized? Zinc or chromium? Anyone? Which one is oxidized? Is it zinc or chromium? So this is your what? Oxidation half reaction, and this is your reduction half reaction. And if you're going to look at this, this is okay in terms of number of elements. Okay? Now, the only way that you need to balance this one is there's a 0 here, there's a +2 here, so you add 2 electrons. So you have their zinc producing zinc 2 plus and 2 electrons. Now this one, on the other hand, you could see there's a 7 oxygen, so it's similar to one that we have earlier. Okay, so you're going to add 7 H2O here, which will result in adding 14H plus here. So if you have it here, 14H plus Cr2O7, 2 minus, producing Cr3 plus and 7 water. And what is missing? You're missing here 6 electrons. So what are we going to do now? Similar to what we did earlier, okay? We're going to put them together. So you have their zinc producing zinc 2 plus. So what is missing here? So you could see here, there's 6 electrons here, there's 2 electrons here. So you need to make this into 3 so that this becomes 6. And once you have that, what will happen? You can add them together, okay? So you have 14H plus Cr2O7 2 minus plus 3 zinc producing Cr3 plus 7 H2O plus 3 zinc 2 plus. So what are you going to do? Check each element. 14 hydrogen, 7 times 2, 14, 7 oxygen, 2 chromium. Okay, oh, the one that's missing here is this one. We forgot. So we have 2 chromium, 3 zinc, 3 zinc. Next, charge. 14 plus 2 will give you what? 14 plus -2. Positive 12. So you have here 2 plus 3 will give you 6. And then 3 times positive 2 will give you 6. So that will give you positive 12 on both ends. So you now say the reaction is balanced. So ask yourself, do you have any question? Do you have any question? So another one, a more challenging one. So you have this reaction, lead ion yields the plumite ion, PbOH3 minus, in basic solution. In turn, this ion is oxidized in basic hypochlorite solution, ClO minus, to lead oxide, PbO2. So balance the equation for this reaction using the half reaction method. So I'm going to use the whiteboard here. So you're going to start Okay, in this reaction, the skeleton reaction, which is what? PbOH3 minus plus ClO minus, producing PbO2, not 3, plus Cl minus. So what are we going to do? Anyone? What are we going to do? We first assign the oxidation number. Okay? We know that it will be a half reaction of this. But the question now, which is oxidized and which is reduced? And we can only do that if we assign the oxidation number. So what's the oxidation number of Pb here? Anyone? What is the sign of hydroxide? Hello. What is the sign of your hydroxide? OH is what? OH minus, right? So that means if you have 3 of that, so you have a -3 here. So that means to have a net charge of -1, what's the charge of your Pb? So your Pb would be +2. You got it? Because why is it +2? So you have 3 of the hydroxide. So that means +2 plus -3 will give you -1, which is that charge. Clear? Now how about the Pb here? What's the charge of the Pb here? Anyone? So what will be the basis that I have here? So I have here an oxygen, and it usually has a charge of what? -2 times 2, that will give me -4. The charge is 0, so that's a +4. So what half reaction is this? Is it oxidation or reduction? Is this an oxidation half reaction or a reduction half reaction? Hello? Anyone who are awake? What is the reaction for the lead here? What is the half reaction for the lead here? Anyone? That is your oxidation. Why? From +2, it becomes +4. Now, on the other hand, what is the charge of the chlorine that we have here? So this is what? Cl minus, so that's a -1. So this is ClO minus. So this is a -2. So this one can only be +1. +1 plus -2 will give you a -1. So that means there's a reduction that happens here. So now we know which is which one is oxidized, which one is reduced. Because the question that you're going to be asked if you're given the reaction may be which of the following species oxidized, which of the following is reduced. So what do we do next? Okay, we balance them. Cl fine, but you have an oxygen here. So the rule that we have is we're going to add it with water. So you add water here, you're going to have 2H plus. Do you follow? Are you still with me? Now on the other side, we'll do the same thing. So the only one that's balanced here is what? Your lead. So what are we going to do? How many oxygen and hydrogen do you have on this side? So you have here 1 oxygen, you have here 3 oxygen. So that means you can add it what? With 2 water. So when you add the water here, so the oxygen is now what? 3. But the hydrogen is what? So you have 3 here, you only have what? 2 times 2, is this 2 times 2? Maybe I'll just add 1 water here, right? Because 2 plus 1 will give me the 3 oxygen that I'm looking for. But my hydrogen is only 2 here compared to the one that's 3 here. So I'm still going to add an H plus. So what else I'm going to do now? I need to balance the charges on both sides. And balancing charges on both sides is by adding electron. So this one is 0. Oh no, this is a -1. So what do we have here? +1. So how many electrons will I add? And in which side will I add the electron? Anyone? Hello. Okay. So if we have this, what we call problem here, so one is -1 and the other is +1. So what we're going to do is we're going to add 2 electrons here. So overall, each of them will have -1 on both sides. Now, how about the other one here? 2 plus and then -1. So that's +1. And this one is -1. So I'm going to add here -1, +1. I'm also going to add here 2 electrons. So what will I do now? I'm going to combine the reaction. So I'm going to just align it so you will see. So which one I can erase? I can erase the 2 electrons. There's 1 hydrogen here, there's 2, so I can remove this, giving you this one. Okay. And then water, none to cancel because you're going to add them. So if you're going to add everything, you have what? PbOH3 minus plus H plus ClO minus producing PbO2 plus Cl minus plus to water. Now the question, how are you going to check if they are balanced? You're going to look at the number of the elements in both of them. So Pb is 1 here, Pb is also 1 here. O is 3 plus 1 makes it 4. So that is 2 here and 2 times 1 here, so that's 4. And then hydrogen here is 3 plus 1 makes it 4. And 2 times 2 will also give you 4. Okay, Cl is 1 on both sides. Now the charge, negative plus positive plus negative will give you -1, which is also the charge that you have here. Hence, this is the balanced chemical equation or balanced redox reaction. So question, before we leave this topic and go to batteries, the main portion that we have here. So we go back to the batteries that we have here. So the next thing that we're going to do is we deal about the so-called electrochemical cell. So those who were there yesterday with me, you notice, or you're able to observe both type of electrochemical cell. The one who performed with this one is the second group. Okay. The first group, you only have a Baltic or galvanic cell when you measure the potential at different temperature. But the second group, you have both the Baltic and galvanic cell, the one that you have different concentration of copper, and an electrolytic cell, that's the one where you use a battery to run the electrolysis of iodine, of Ki. So when you have an electrochemical cell, okay, this is a system consisting of electrons that dip into an electrolyte and in which a chemical reaction either use or produce an electric current. So the one that produce electric current, that's your Baltic or galvanic cell. How do you remember? This is named after Alessandro Volta, and this is named after Luigi Galvani, the basis for the Frankenstein science that they have. Okay, so galvanic or Baltic cell, this is an electrochemical cell in which a spontaneous reaction generates an electric current. An electrolytic cell, on the other hand, this is an electrochemical cell which an electric current drives an otherwise non-spontaneous reaction. And if you're going to look at what is happening, especially in a Baltic or galvanic cell, this is what happened. The electrons flow through an external circuit from the zinc electrode to the copper electrode. So the way that you're going to do this, your zinc electrode there, that serves as your anode, and your copper electrode, that serves as your cathode. And in between them is the salt bridge. So you see, it's just as what we call Michael Jackson's on ABC. The electron travels alphabetically from the anode through the salt bridge to the cathode, right? There's a Michael Jackson song or Jackson 5 song, ABC, 1, 2, 3. Okay, so the same thing that you have here. Okay, the ions flow through the salt bridge to maintain the charge balance. So I'm just showing to you here how the electrode looks like. The setup that we don't have yesterday is the bulb, but instead of what we call measuring the potential that you have there, the endpoint is what we call the bulb. You'll be able to produce light on the bulb. Okay, so this is what's happening. Your zinc metal there, after some time, it will deteriorate because your zinc metal is oxidized to give you zinc 2+. Now your copper 2+, on the other hand, what it do, it's electrodeposited to form what we call copper. So after some times, you will see there your copper being more shiny because new copper metal is deposited. Now you may ask yourself, if the zinc is converted here to zinc 2+, which gives you what? A net charge of a positive sign, and here your copper 2+ is lost, which gives you a charge of a negative sign. Okay, how does electron neutrality achieve? So that's where the salt bridge comes into being. So since this becomes negatively charged, why? Because the electrons are accumulated here. This system gained the electron. The positive charge of your salt bridge goes there. And then since you lose the electrons here, the negative charge, okay, you lose the electron, it becomes positive. The negative charge of the salt bridge comes in. So that's what the function of your salt bridge, to maintain electron neutrality. Okay, so if we're going to look at the details that that we have in terms of the galvanic cell, the salt bridge is the tube of electrolyte in a gel that is connected to 2 half cells of the Baltic cell. It allows the flow of ions but prevent the mixing of different solutions that would allow the direct reactions of the cell reactant. So in the salt bridge, your cation move toward the cathode, and the anions move toward the anode. So what is the anode and what is the cathode? So anode is the electron where oxidation takes place. Cathode is the electrode where reduction takes place. And as I've told you, electrons flow, okay, from anode to cathode. Electrons flow alphabetically. So those are some of the basic concepts that you should learn and expect to be asked during the exam. So instead of the bulb, what did you do yesterday? We just measure the potential. And this potential is enough to light up a bulb. Okay? So the difference that we have yesterday, you have an extra beaker that contains your salt bridge, but you can have a salt bridge like this one. So what you have there, you have here a salt. And it bridges both the cathode and the anode. Okay? So if ever you're asked to do this thing, construct 1/2 cell of a voltage by inserting a copper metal into a solution of copper sulfate, and then the other one's aluminum into aluminum nitrate. So what you're going to do here, okay, you have to determine which is the anode and which is the cathode. Why did we say zinc is the anode and copper is the cathode? That's what you're going to learn in the succeeding slide. Okay, how do we know which is the anode and which is the cathode? So if we're going to do this one, we have a copper here. So what will happen? Your aluminum is the anode, and then your copper is the cathode. So if you're asked what is the direction of your electron, it is from the anode to the cathode. So you already see two instances here where copper served as the cathode. Now you may ask yourself, how are we going to know if the metal will be the anode and the cathode? Okay, so another way, before we answer that question, which is the anode and which is the cathode, let's try to see how do we write a battery. So usually we use the so-called cell notation. So a voltage cell notation is just a shorthand method describing a voltage cell. And the way that you write it is just ABC. The anode is on the left side and the cathode is on the right side. How do we write our cell? It's from left to right, right? Do we write from top to bottom? I don't know if I'm right. Are the Japanese like that, from top to bottom, when they write those characters? But we always write from left to right, right? We read from left to right and then top to bottom. Am I right? So the same thing with the battery. Okay, when you write the notation there, you also follow. Okay, it's written from left going to the right. The left is the oxidation, the right is the reduction. And if ever we do it like this, so the third terminal is written on the outside, left for the anode, right for the cathode. And phase boundary are shown with a single vertical bar. So if we have the zinc as our what we call anode, we write it this way. And if we have the copper, we write it this way. Okay, so if we have a notation for a battery, we have it like this. Now, what divides them? The two vertical bar, and that's denote the salt bridge. You need to learn this one because you might be given here and you're asked to interpret what it means, or you're given a reaction and you're asked for the cell notation of that reaction. Okay, so for instance, what does this mean here? So when a hot reaction involves a gas, the electrode is an inert material such as platinum. So every time there's a difference in their what we call state, you put that vertical bar. Okay. So because this is a reduction, it appears on the right side. And then the oxidation of H2 to H plus. Okay. You also have a platinum here. So the notation that you have there is on the far left because that is an oxidation reaction. So if you're going to write them, you end up as writing it like this. So that's the cell notation for this one. And you can also have a cell notation here. So if you have a cell notation here, if you're asked which one is oxidized, what is your answer? Which is reduced? Anyone? What specific species was oxidized? Hello? Anyone? If you're asked a question like this one, what is your answer? Which is oxidized? Your answer will be copper. Which is reduced? Your answer specifically F2. Okay, so those are the information that a cell notation will give you. So if you're going to look at the cell notation for a Baltic cell like this one, you're asked what will be the cell reaction. So how are you going to write it? You just follow that reaction. So this is oxidation. So and the other one will be now the question, are they balanced? Are they balanced? The answer is no, because you have 3 electrons here and you have 2. So what do? You multiply it by 2 here, and you multiply this by 3. Why? So that this becomes 6 electrons. So I think I made a mistake. That should be copper 2 plus 2 electron, and then copper. And then you multiply that by 3. So you will end up with what? 3, 6, 3, and you have 2, 2, 6. And the overall reactions that you have there would be 2Als plus 3 copper 2 plus, producing 2Al 3 plus 3 copper. Question? Hello? Are you still there?
Yes.
Just like a spirit of the glass.
Yes.
Are you there?
Could you just explain why in between the aluminum and the copper, why there's 2 lines?
That's the salt bridge.
Oh, okay.
So this is your anode. This is your cathode. So in the anode, you have the oxidation that takes place, which is this one. And in the cathode, you have the reductions that takes place. Okay?
Thank you.
Now, the cell potential. So it says that the maximum potential difference between the electrons of Baltic cell is called the cell potential or the electromotive force. So that's the one that you see in your, what do you call that, voltmeter? Okay, or the one that we have yesterday, that's the one that is measured by the Lager. And that's what we call cell potential, electromotive force. Okay, there are different terms for that. And this cell potential that we have, you can measure it with a digital voltmeter. So usually, if it's being produced, that corresponds to what we call work. That's what the battery is generating the energy generated by a given what we call battery. Okay, and if we're going to look at this cell potential, so let's say if we have a cell potential of 0.5 volts, so that means the cell reaction of this one, okay, that's the amount that is generated. And if you're asked what's the maximum electrical work of this if you obtain it in 1 gram, so all you need to do is determine what's the corresponding moles of this so-called 1 gram in terms of this aluminum. So you have this formula here, NFE cell. Okay, so if we're going to what we call look at the reactions that we have here, so we just follow this work equals to negative NFE cell. So we have here what? The cell potential, which is 0.5, okay? And then N here is the number of electrons that is involved. How many electrons are involved here if you go to our previous reaction? Anyone? What is the value of N? If we're going to look at the previous example that we have here, so we have 6 electrons. So that means the value of that is 6. Okay. Now, you have here F. What does F means? That is your Faraday constant. And that is equals usually to a number that for now we're going to put as 96,485 coulomb per mole. So N is that, F is that, and E cell there, that's your 0.5 volts, which is just equals to joules per coulomb. So what is the mass that we have here? What is the maximum work that we can get from this one? So you cancel the coulomb. So you have here joules per moles, right? So what is the number that you have there? So we can cancel the moles there because the moles is this one, 6 moles of electron. So the amount that you have there, that's the amount that you produce when you have this reaction. What's the number that you get? Anyone? 6 times 96,485 times 0.5. So that is around 2.89 times 10 to the 1, 2, 3, 4, 5 joules. That's the corresponding maximum work that you can do. Question. Before we go to how do we get the electron potential? So this is just using this one. NFP cell that's equals to the maximum work. So how do we get the cell potential? Okay. So cell potential here is a measure of the driving force of the cell reaction. So usually it is composed of the two half reaction, the oxidation potential for the oxidation half reaction at the anode and the reduction potential for the reduction half reaction at the cathode. So if you're going to look at here, E cell is just equals to the oxidation potential plus the reduction potential. And if you're talking about the reduction potential, that's just the negative of the reduction potential. How do we look at this? Okay, so we have a table here. We just look, I'm just going to go back right away here in the table. So look at the table here. This is what we call the reduction potential table. Why do you think I call it why do you think it's called reduction potential table? Anyone? Why do we call this the reduction potential table? Anyone?
Because it has the values. Like,
is it the volume? What
values.
else?
And the half reactions.
What is the half reaction?
Of reduction.
Okay. We call it the reduction potential because the reaction is reduction. Everyone agree that this is a reduction reaction? How do I know it is a reduction reaction? Anyone? Why do you think this is a reduction reaction? What tells me that this is a reduction reaction? Anyone?
That is losing electrons.
Again?
That it's losing electrons. Like for example,
is that how we define reduction? How do you define reduction? How do you define reduction, or how do you find oxidation? Because it seems to me now you don't know what is a reduction and what is a oxidation. What does this mean? Anyone?
gain of electrons, sorry.
Okay. So if you gain an electron, where do you expect the electron in the reaction? Is it in the reactant or the product? Okay. So whenever you have an electron in the reactant, that means you gain an electron. Whenever you have an electron in the product, that means you lose. Does that make sense? Now, as I have told you, we call this a reduction potential because indeed it's based on reduction reaction. Now, what happens if you reverse the reaction? So when you reverse the reaction, what will happen to this one? LiS producing Li plus electron. So this now becomes oxidation. And what happened to the value that we have here? This now becomes positive. I want you to make sure you understand this one because this is not what we call a half point thing. Either you get it or you don't. And this is where a lot of, we could say, confusion comes in. So the best way for you to avoid that confusion, you have to know when a reaction is written, you have to know if it's reduction or oxidation. Because if you don't understand what's an oxidation or what's a reduction, I think you cannot move on further. Okay? And I can tell you, the third exam is the most challenging exam that we have. Okay. Now, what does it tell us here? The oxidation potential that you have here, that's just the reverse of whatever the value that you have in the reduction potential. Because one way that I'm teaching you how to get the cell potential is the potential when the reaction is oxidized plus the potential when it is reduced. Because if you're going to look at this, the E cell that we have here is just equals to the E anode plus E cathode. But this is oxidation potential, and this is reduction potential. So what does it mean now? I'll try to see what's the next one here. Okay, so we're going to go back to this table. So what do we have here? So if we have the cell potential, one way for you to do is whatever the oxidation potential that you have here added with the reduction potential that you have. And the way that you do this one is the E oxidation is equals to the negative of the potential in the anode. So whatever the reduction potential that you have in the table, you're going to get the opposite sign of that. So the way that they look at it, so E cell is just equals to this. The negative of the anode plus the positive of the cathode potential. Or the way that they look at this, whatever is the potential in the cathode minus the potential that you have there in your anode. Okay? So what does this mean? Let's go with copper and zinc. So this is now, how do we know that zinc is the anode and the copper is the cathode? So I want you to look at the table here. I want you to help me find where is the copper and where is the zinc. I hope it's here. I think it's here. So I have here the zinc and I have here the copper. There's two copper. So the one that I have is this one. Okay. Now, look at the value that we have here, 0.76 negative. And we have here 0.34. So what is the rule? When you have two reactions that you want to form a battery, the one with the higher reduction potential will remain in reduction form. And when you are in the reduction form, what is your electron called? That's your cathode. And this one will be your anode. Why? What happened? The one that has less reduction potential, that's the one that will undergo oxidation. Okay? So remember, between the copper and the zinc, anode is assigned to the zinc. Why? Because negative 0.76 is lower than 0.34. So between the two, this will remain reduction. This will become oxidation. Does that make sense now? Why zinc is the anode while the other one is the cathode? Because zinc has a lower reduction potential. So it will undergo oxidation. So if it undergo oxidation, what happened to this? This reaction will reverse. What's the other example that we have where copper remains as what we call cathode and the other one is anode? I think we have the aluminum. And the main issue on that also has something to do with the potential. The reduction potential is lower than the one in the copper. So aluminum will undergo oxidation and that will be your anode compared to this one, which undergo reduction, and this will be your cathode. Let's see if you understand. So what if I have an Fe3 plus, okay, reacting with what we call a nickel 2 plus, which is the anode and which is the cathode between the two? Fe3 plus reacting with 3 electrons and nickel 2 plus reacting with 2 electrons. Let's see. Which is the anode and which is the cathode? Anyone? We'll not move on unless you show me that you understand. And instead of meeting 2 more times, we're going to meet 3 more times. So which is the anode and which is the cathode? If you have a system where you have an iron metal dip in an iron solution, iron 3 plus, okay, with a nickel metal dip in a nickel solution. So which is the anode? Put in the chat. Is the anode iron or nickel? Anyone who are awake? Which do you think is the anode and which do you think is the cathode? The answer is there straight in the table. So what are you comparing? You're comparing this value with what? This value. So which is the anode? Nickel or iron? Which is the cathode? How about the others? What the hell are you saying copper? We're talking about iron and nickel. We're talking about this and this. So which is anode? Anyone? So if you're going to look at the value here, so negative 0.04 and versus negative 0.023. So this is higher compared to that one. So this becomes your cathode. And it remains in the reduction reaction form. While this one, which is lower, that becomes your anode and it will undergo oxidation. Okay, so those are the stuff. I'm just trying to see if you understand the concept, which one is the anode and which one is the cathode. Okay. I'm just trying to look at the other stuff that we have here. Because the next thing that we're going to do, okay, we have this table. How in the hell this table came up in the first place? Surely it was not invented out of nowhere. There's always a basis that they have there. Yes. And what is the basis that they have in constructing this table? So what they do, okay, each of them is what we call a half cell reaction. So you have this what we call one half cell reaction, and you have another half cell reaction, and then all you need to do is combine it to get you the numbers. But the question now is, what is the standard that they use? Which do you think is the standard here? Anyone? Or maybe I'll clean it up. So which do you think is the standard that they use here? I can always say see it right away because it has a distinct markings on it. Why do you think this one is highlighted? So those values, you obtain it when you compare each of them with this. So what do you have here in the system? An acid and a hydrogen. So depending whether they're stronger than the other half reaction or weaker than the other half reaction, it will generate a number. Why? What do you think the value if we reverse the reaction? Anyone wants to have a wild guess? What do you think the value when I reverse the reaction that we have here? Anyone? Oops.
Wouldn't it be 0 still?
Okay. How about the others?
I
Okay.
agree.
What do you think is the value if I reverse the reaction? Yes, it's 0. Okay. That's the standard that they have. So everyone here, they react it with the hydrogen system and they look at the number that come out. So this is what we have in the succeeding slide that we have here. So when they put the zinc electrode with the HCl and the hydrogen gas there, it gives you this one, 0.76. But in this way, this is the anode and this is the cathode. But look what happened. If I put it with the copper, it gives me this value, but there's a difference there. This is the cathode and this is the anode. So what does this mean? Between zinc and the hydrogen, okay, hydrogen is stronger than zinc because it caused the zinc to oxidize. But between hydrogen and copper, copper is strong in terms of reducing agent. Okay, hence giving you this value. So if you're going to follow this one, this is usually, if you put it in a reduction potential form, this is a positive 0.34. But this one, okay, if you're going to put it in the reduction potential, that's a minus 0.76 as shown. I think I have another table here, like here. So you have here negative 0.76, and then you have here as what we call positive 34. Where's that? So what information you can get here? Okay, so the cell potential is written as the reaction is given. The more positive your cell potential is, the greater the tendency for the substance to be reduced. And the half cell reactions are reversible. So if you reverse it, you're going to get the negative sign. So the sign of the cell potential changes when the reaction is reversed. And changing the stoichiometric coefficients of half cell does not change the value of the cell potential. So this is an internal property. So what is an internal property? Whatever the amount, their value is the same. Like density, it's always 1 gram per ml for water. Okay? So that's why whenever you're given two half cell reaction, the first thing for you to look at is how you're going to predict which is the anode and which is the cathode. And we're going to continue on that next week because it's almost 1:30. And I have an announcement that I need to let you know. Okay, so I have already talked with Dr. Macy's. So you will have your makeup exam on April 20. And you will have your third exam on April 22. Okay? And then you will have your final exam on April 29. So those are the schedule that we have. And then an additional schedule that you will have, your quiz for chapter 17 will be posted by tonight. And you have until Thursday to answer them before our class. And then 18 might be up during the weekend until Tuesday next week. And then chapter 19 may be up by next week until Thursday. Because depending on how fast that we're going to do, we're not sure if we're going to meet on April 15. It depends on how we do on Thursday. So question.
Is the 2 hours